Welcome to 1256 of the H series. We are currently experiencing an incident of sunlight. Glad to be here to record this odd incident. It is almost like the quantum experiment. I haven't seen the sun in 2 weeks, to be honest. Thanks to the warm weather, it's been cloudy every day. Now it's changing into more normal November temperature, which I'm very happy for. I will continue where I left up in 1255. It is a tough nut to crack though. Give it some patience, it will help your understanding of everything, as I said before. But there is no use using directly depiction of space anymore. We need to do something else, and that is to make graphs. And I hope you understand why there is no use to make depictions, because also the depictions are under the limitations of the smallest possible space is the Planck constant. This is vaguely similar to how we described space to be fractal before, but it helps to understand that. The edginess and the discreteness. Discrete is the opposite of linear. Discrete is the opposite of continuum. Discrete is these continuous pieces of space and time. I'd say that changes everything. For simplicity, we often draw the graphs in 2 dimensions, even that be very hard to understand. What would dimensions be if space is discrete? Yeah, it's a mind blower as well. So if you feel dizzy, pause the video or simply don't watch it. It could be too much, actually. It is a developing headache in my head as well, so I do understand you. I feel compassion with that. Don't press yourself too much. For simplicity, on page 71 in the article from Scientific American, we often draw the graphs in 2 dimensions, but it is better to imagine them filling 3-dimensional space, because that is what they represent. Yet there is a conceptual trap here. The lines and nodes of a graph do not live at a specific locations in space. Each graph is defined only by the way its pieces connect together and how they relate to well-defined boundaries, such as boundary B. The continuous 3-dimensional space that you are imagining the graphs occupy does not exist as a separate entity. All that exist are the lines and nodes. They are space. And the way they connect defines the geometry of space. These graphs are called spin networks because the numbers on them are related to quantities called spins. Roger Penrose of the University of Oxford first proposed in the early 1970s that spin networks might play a role in the theories of quantum gravity. We were very pleased when we found in 1994 that precise calculations confirmed his intuition. Readers familiar with Feynman diagrams should note that our spin networks are not Feynman diagrams, despite their superficial resemblance. Feynman diagrams represent quantum interactions between particles, which proceed from one quantum state to another. Our diagrams represent fixed quantum states of spatial volumes and areas. The individual nodes and edges of the diagrams represent extremely small regions of space. A node is typically a volume of about 1 cubic Planck length, and a line is typically an area of about 1 square Planck length. But in principle, nothing limits how big and complicated a spin network can be. If we could draw a detailed picture of the quantum state of our universe, the geometry of its space as curved and warped by the gravitation of galaxies and black holes and everything else, it would be a gargantuan spin network of unimaginable complexity with approximately 10 to the 184 nodes. These spin networks describe the geometry of space. But what about all the matter and energy contained in that space? How do we represent particles and fields occupying positions and regions of space? Particles such as electrons correspond to certain types of nodes, which are represented by adding more labels on nodes. Fields such as electromagnetic fields are represented by additional labels on the lines on the graph. We represent particles and fields moving through space by these labels moving in discrete steps on the graphs. Moves and foams. Particles and fields are not the only things that move around. According to general relativity, the geometry of space changes in time. The bends and curves of space change as matter and energy move, and waves can pass through it like ripples on a lake. In loop quantum gravity, these processes are represented by changes in the graphs. They evolve in time by a succession of certain moves in which the connectivity of the graphs changes. When physicists describe phenomena quantum mechanically, they compute probabilities for different processes. We can do the same when we apply loop quantum gravity theory to describe phenomena, whether it be particles and fields moving in the spin networks or the geometry of space itself evolving in time. In particular, Thomas Cheeman of the Perimeter Institute for Theoretical Physics in Waterloo, Ontario, has derived precise quantum probabilities for the spin network moves. With these, the theory is completely specified. We have a well-defined procedure for computing the probability of any process that can occur in a world that obeys the rules of our history and our theory. It remains only to do the computations and work out predictions for what could be observed in experiments of one kind or another. Einstein theories of special and general relativity join space and time together into the single merged entity known as spacetime. The spin networks that represent space in loop quantum gravity theory accommodate the concept of spacetime by becoming what we call spin films. With the addition of another dimension, time, the lines of the spin networks grow to become two-dimensional surfaces, and the nodes grow to become lines. Transitions where the spin networks change are now represented by nodes where the lines meet in the film. The spin film picture of spacetime was proposed by several people, including Carlo Rovelli, John Barrett, and others. In the spacetime way of looking at things, a snapshot at a specific time is like a slice cutting across the spacetime. taking such a slice through a spin foam produces a spin network. But it would be wrong to think of such a slice as moving continuously, like a smooth flow of time. Instead, just as space is defined by a spin, network's discrete geometry, time is defined by the sequence of distinct moves that rearranged the network, as shown in the illustration on the opposite page. Picture depicted here. You'll find it in the folder. In this way, time also becomes discrete. Time flows not like a river, but like the ticking of a clock, with ticks that are about as long as the Planck time, or more precisely, time in our universe flows by the ticking of innumerable clocks. In a sense, every location in the spin foam where a quantum move takes place, a clock at that location has ticked once. Predictions and tests. I have outlined what loop quantum gravity has to say about space and time at the Planck scale. But we cannot verify the theory directly by examining space-time on that scale. It is too small. So how can we test the theory? An important test is whether one can derive classical general relativity as an approximation to loop gravity, loop quantum gravity. In other words, if the spin networks are like the threads woven into a piece of cloth, this is analogous to asking whether we can compute the right elastic properties for a sheet of material by averaging over thousands of threads. Similarly, when averaged over many Planck lengths, do spin networks describe the geometry of space and its evolution in a way that agrees roughly with the smooth cloth of Einstein's classical theory? This is a difficult problem, but recently researchers have made progress for some cases. For certain configurations of the material, so to speak, for example, long wavelength gravitational waves propagating on otherwise flat space can be described as excitations of specific quantum states by the loop quantum gravity theory. Another fruitful test is to see what loop quantum gravity has to say about one of the long-standing mysteries of gravitational physics and quantum theory, the thermodynamics of black holes. In particular, their entropy, which is related to disorder. Physicists have computed predictions regarding black hole thermodynamics using a hybrid approximate theory in which matter is treated quantum mechanically, but space-time is not. A full quantum theory of gravity, such as loop quantum gravity, should be able to reproduce these predictions. Specifically, Jacob D. Bekenstein infer that black holes must be ascribed an entropy proportional to their surface area. Shortly after, Stephen Hawking deduced that black holes, particularly small ones, must emit radiation. These predictions are among the greatest results of theoretical physics in the past 30 years. To do the calculations in loop quantum gravity, we pick the boundary B to be the event horizon of a black hole. When we analyze the entropy of the relevant quantum state, we get precisely the prediction of Bekenstein. Similarly, the theory reproduces Hawking's prediction of black hole radiation. In fact, it makes further predictions for the fine structures of Hawking radiation. If a microscopic black hole is ever observed, this prediction could be tested by studying the spectrum of radiation it emits. That may be far off in time, however, because we have no technology to make black holes small or otherwise. Indeed, any experimental test of loop quantum gravity would appear at first to be an immense technological challenge. The problem is that the characteristic effects described by the theory become significant only at the Planck scale, the very tiny size of the quanta of area and volume. The Planck scale is 16 orders of magnitude below the scale proved in the highest energy particle accelerators currently planned. Because we cannot reach the Planck scale with an accelerator, many people have held out little hope for confirmation of quantum gravity theories. In the past several years, however, a few imaginative young researchers have thought up new ways to test the predictions of loop quantum gravity that can be done now. Wow! These methods depend on the propagation of light across the universe. When light moves through a medium, its wavelength suffers some distortions, leading to effects such as bending in water, the separation of different wavelengths or colors. These effects also occur for light and particles moving through the discrete space, described by a spin network. Unfortunately, the magnitude of the effects is proportional to the ratio of the Planck length to the wavelength. For visible light, this ratio is smaller than 10 to the minus 28. Even for the most powerful cosmic rays ever observed, it is about 1/1000th. For any radiation we can observe, the effects of the granular structure of space are very small. What the young researchers spotted is that these effects accumulate when the light travels a long distance, and we detect light and particles that come from billions of light years away. From events such as gamma ray bursts a gamma ray burst spews out photons in a range of energies in a very brief explosion. Calculations in loop quantum gravity by Rodolfo Gambini and others predict that photons of different energies should travel at slightly different speeds and therefore arrive at slightly different times. We can look for this effect in data from satellite observations of gamma ray bursts. So far the precision is about a factor of 1,000 below what is needed. But a new satellite observatory called GLAST, planned for 2006, will have the precision required. The reader may ask if this result would mean that Einstein's theory of special relativity is wrong when it predicts a universal speed of light. Several people, including Giovanni Amelino Camelia, and João Manguejo of Imperial College London, as well as myself, have developed modified versions of the Einstein theory that will accommodate high energy photons traveling at different speeds. Our theory proposed that the universal speed is the speed of very low energy photons, or equivalently long wavelength light. Another possible effect of discrete spacetime involves very high energy cosmic rays. More than 30 years ago, researchers predicted that cosmic rays with an energy over this limit but it turns out that the more than 30 years ago, researchers predicted that cosmic ray protons with an energy greater than 3 × 10⁻⁹ electron volts would scatter off the cosmic microwave background that fills space and should therefore never reach the Earth. Puzzlingly, a Japanese experimenter called Agasa has detected more than 10 cosmic rays with an energy over this limit. But it turns out that the discrete structure of space can raise the energy required for the scattering reaction, allowing higher energy cosmic ray protons to reach the Earth. If the Agasa observations hold up, and if no other explanation is found, then it may turn out that we have already detected the discreteness of space. The cosmos. In addition to making predictions about specific phenomena, such as high energy cosmic rays, loop quantum gravity has opened up a new window through which we can study deep cosmological questions, such as those relating to the origins of our universe. We can use the theory to study the earliest moments of time, just after the Big Bang. General relativity predicts that there was a first moment of time, but this conclusion ignores quantum physics. Recent loop quantum gravity calculations by Martin Bujold indicates that the Big Bang is actually a big bounce. Before the bounce, the universe was rapidly contracting. Theorists are now hard at work developing predictions for the early universe that may be testable in future cosmological observations. It is not impossible that in our lifetime we could see evidence of the time before the Big Bang. A question of similar profundity concerns the cosmological constant. A positive or negative energy density that could permeate empty space. Recent observations of distant supernovae and the cosmic microwave background strongly indicate that this energy does exist and is positive, which accelerates the universe's expansion. Loop quantum gravity has no trouble incorporating the positive energy density. This fact was demonstrated in 1990 when Hideo Kodama wrote down equations describing an exact quantum state of a universe having a positive cosmological constant. Many open questions remain to be answered in loop quantum gravity. Some are technical matters that need to be clarified. We would also like to understand how, if at all, special relativity must be modified at extremely high energies, so far as speculations on this topic are not solidly linked to loop quantum gravity calculations. In addition, we would like to know that classical general relativity is a good approximate description of the theory for distances much larger than the Planck length in all circumstances. Finally, we would like to understand whether or not loop quantum gravity has anything to say about unifications. Are the different forces, including gravity, all aspects of a single fundamental force? String theory is based on a particular idea about unification, but we also have ideas for achieving unification with loop quantum gravity. Loop quantum gravity occupies a very important place in the development of physics. It is arguably the quantum theory of general relativity, because it makes no extra assumptions beyond the basic principles of quantum theory and relativity theory. The remarkable departure that it makes, proposing a discontinuous spacetime described by spin networks and spin phones, emerges from the mathematics of the theory itself, rather than being inserted as an ad hoc postulate. Still, everything I have discussed is theoretical. It could be that in spite of all I have described here, space really is continuous, no matter how small the scale we probe. Then physicists would have to turn to more radical postulates, such as those of string theory. Because this is science, and in the end, experiment will decide. The good news is that this decision may come soon. I say thank you very much. It was a pleasure reading this article. Here we have it. And now I can actually wish you a very pleasant afternoon. And still, the sun is coming and going. And you can see the Ferris wheel, and you can see the grey sky. It's beautiful, just that we had enough. Every day is too much beauty, isn't it? Thank you very much, and have a very pleasant afternoon.